Have you ever stared at a chemical equation and just felt stuck? Like you're trying to solve a puzzle with pieces that just don't fit? Well, today we are going to tackle one of the trickiest kinds out there, balancing redox reactions. Yeah, that's short for reduction oxidation. It's where electrons are literally jumping between atoms. And I promise, by the time we're done here, you'll see it's not magic. It's all about having the right strategy. Just take a look at this. You've got a permanganate ion reacting with an iron ion. At first glance, it's kind of a mess, right? The atoms don't line up, the charges are all over the place. You can't just count the atoms on each side like you do in the simple stuff. So, where do you even begin? And this isn't just some random textbook problem. This is real-world stakes. Imagine a geologist out in the field, analyzing a sample of iron ore. She's using this exact reaction. And to get a measurement she can actually trust, the equation has to be perfectly, absolutely balanced. Precision is everything. All right, so here's our game plan. First, we'll get a handle on the challenge itself. Then we're going to add two super powerful tools to our toolkit. One is all about following the electrons, and the other is a classic divide and conquer approach. We'll even see how to tweak them for different situations, and then we'll wrap it all up. You know, with a reaction this complex, just guessing and checking is a complete non-starter. It'll get you nowhere. We need a system. This is where a chemist's real balancing act begins. So our first tool is called the oxidation numbers method. Think of this as like chemical accounting. We're going to assign a special number to each atom so we can track exactly where the electrons are moving. It's all about following the money, or, in this case, the electrons. Okay, let's dive right in. Here are the 6 steps for this first tool. I know, it looks like a lot, but trust me, it's a totally logical flow. We're going to walk through each one using our geologist's problem. Okay, step 1, we assign something called an oxidation number to each atom. It's kind of like a charge, and it helps us track electrons. So if we look at our equation, we see manganese goes from a +7 state down to +2. To do that, it had to gain 5 negative electrons. That process, that's called reduction. Meanwhile, iron goes from +2 up to +3. It lost an electron, and we call that oxidation. Now, here is the absolute key to everything. The electrons have to balance. The number of electrons lost has to equal the number gained. There's no other way. So if our manganese atom is gaining 5 electrons, where did they come from? Well, that's why we need 5 iron atoms, each losing 1 electron, to make the whole exchange perfectly even. And we show that by popping a 5 right in front of the iron on both sides. We are so close. The manganese and the iron are balanced, but what about those oxygens? See the 4 oxygens on the left? Well, because this reaction is happening in an acidic solution, we have a trick up our sleeve. We can use water molecules, H2O, to balance them out. So we add 4 water molecules to the right. But wait, now we have 8 hydrogens on the right. No problem, we just balance that by adding 8 hydrogen ions, H+, to the left side. And here's the part you can never, ever skip. Check your work. This little table confirms everything. 1 manganese, 5 irons, 4 oxygens, 8 hydrogens, all perfectly balanced on both sides. But here's the real test. Look at the bottom line. The total electrical charge on the left is +17. The total charge on the right, also +17. Boom, it is perfectly balanced. All right, let's look at our second tool. It's called the half reactions method. And if that first method was like doing all the accounting at once, this one is pure divide and conquer. We're going to split this big, messy reaction into 2 smaller, much easier parts. The game plan here looks a little different, but it's just as powerful. We're going to break the equation into its 2 halves, the oxidation part and the reduction part. We'll balance each one all by itself, for both atoms and charge, and then we'll smash them back together at the end. It's a very focused, piece-by-piece strategy. Okay, so first, we just pull the original equation apart. The oxidation half is super simple. Iron loses an electron. The reduction half is where manganese gains them. And just like we did before, we use our trusty water and hydrogen ions to get the oxygens and hydrogens balanced in that reduction half. So now we add the electrons themselves into the picture to balance the charge in each separate half reaction. For the iron, we add 1 electron to the right side to make both sides have a +2 charge. For the manganese half, we need to add 5 electrons to the left side to get both sides down to a +2 charge. We are now explicitly showing where those electrons are going. And here's where it all comes together. Do you see the problem? The manganese half needs 5 electrons, but the iron half is only giving away 1. That won't work. So the fix is easy. We just scale up the iron reaction.
We multiply that whole thing by 5. Now, 5 electrons are lost and 5 electrons are gained. The exchange is equal, so we can add the two halves together and the electrons just cancel each other out. And would you look at that? It's the exact same balanced equation we got with the first tool. We took two completely different paths, but they led to the exact same correct answer. One method is kind of a big picture view, the other is more step by step. It really just comes down to choosing the tool that makes the most sense to you.
Now, what's really cool is that these methods are also super flexible. So far, we've been working in an acidic solution, right? That's why we were using those H+ ions. But what if your reaction is happening in a basic solution? Turns out it just takes one tiny adjustment.
Here's the cheat sheet. If you're in a basic solution, you start by doing everything we just did. Seriously, just pretend it's an acid. Then, at the very end, you look at how many H+ ions you have. For every single one, you add one hydroxide ion, that's OH-, to both sides of the equation. The H+ and the OH- will combine to make water, and then you can just tidy everything up. It's this one last clever step.
Okay, let's wrap this up. I want to take a step back and think about what we've really done here. Because we didn't just balance an equation, we learned a new way to think about a problem.
You know, this line from the source material really just says it all. It doesn't matter which tool you pick, the oxidation numbers or the half reactions. What matters is that you have a logical, step-by-step process that you can trust to get you to the right answer every single time.
And that's the real takeaway here. This is so much bigger than a chemistry lab. This is a powerful form of problem solving. It's about looking at a complex, messy system, breaking it down into manageable parts, applying a consistent set of rules, and building your way to a clear, correct solution.
So, that leaves me with one final question for you. Think about it. Whether you're trying to debug a piece of code, or plan a big project, or even just understand a really complicated argument, what other complex systems in your life could suddenly become simple if you just had the right tools to take them apart? Thanks for joining me.